To complete a lab assignment, do every task in the lab report outline. There is one-to-one matching between the list of tasks and the lab guide app items. This Lab 6 has at least 2 circuits to be connected together and tested as a single unit. Hence, it is necessary to consider the space allocation of both on a circuit board. The first circuit, to be studied in Part A, is the high-pass filter as highlighted in light blue. Its output will be coupled to the low-pass filter, highlighted in green. The joint circuits perform as a band-pass filter, whose functions are to be tested with a signal simulation circuit that generates a test signal for the band-pass filter. Lastly, to evaluate the performance of the band-pass filter, its output will be processed by a receiver demodulator circuit. In addition, space allocation should also be considered for the connection of the circuit to the DG lent AD2 for measurements. Consider a pure sinusoidal signal input to a circuit. When its frequency f changes, the amplitude of the output signal from a linear circuit can do 3 things: it can increase, it can decrease, or it can stay the same. This behavior can be determined by calculating the output signal. The solution of circuit B, high-pass filter, is given here. The output behavior versus frequency is determined by its amplitude term. The key parameters of the amplitude are the 2 complex numbers Z1 and Z2, that depend on the resistances and capacitances of the circuit. Let's take a look at the output amplitude term. Notice that there are the f² terms in the expression for the output amplitude. Hence, the circuit is said to be of the second-order type. This is different from the circuits of Lab 5, where only first order of f appears in the expressions of the outputs. This is log-log plot of the magnitude of the amplitude as a function of frequency, known as Bode plot. It goes to 0 as frequency goes to 0, which means that unless a signal oscillates, it has 0 output. On the other hand, if the frequency is above approximately 3 kHz, the output magnitude is constant and equal to the input. This behavior, which involves the blocking and attenuation of signals with low frequencies, but allowing high-frequency signal passing through, is called high-pass filter. One last important point is the manner the magnitude decreases versus frequency. Because of the frequency squared term in the numerator, if the frequency decreases by a factor of 10, the output magnitude decreases by a factor of 100. Thus, the higher order a filter is, the more efficient it is in blocking signals of unwanted frequencies. If you have learned Laplace transformed circuit theory, then you are aware how the combination of various capacitances and resistances determine the 2 critical complex numbers, known as roots, Z1 and Z2 in the output amplitude denominator. The 2 roots are shown as the points in the graph of the complex plane. These roots are what determine how oscillatory or how damped the circuit response will be, with respect to a spike, or an abrupt change of the input, also known as the step or impulse response. This affects the circuit performance in the presence of step or spiky noises. How it responds is a matter of choice for the circuit designer, for whichever applications. The next slide offers more insight in the circuit response behavior in order to design the configuration of the roots in the complex plane. This animation shows the 3D plot of the output amplitude, also known as transfer or frequency response function, versus complex frequency. The 3D plot shows that the closer the roots are to the real axis, the sharper the peak of natural frequency response of the circuit, known as the resonance frequency, and the circuit has a highly oscillatory response with a step input. Conversely, the further the roots are away from the real axis, the more damped the circuit response becomes. Oscillatory behavior is associated with fast response. Damped behavior is associated with slow response. The balance between oscillatory behavior and fast, versus damped behavior and slow, is a matter of design choice for particular applications. In this Lab 6, it is designed for a slight oscillatory behavior in order to learn about resonance behavior. This app provides a simulation of the output signals. Consider the high-pass filter. The app can be used as a sanity check for the circuit response measurements with sinusoidal and square waves. As frequency increases from below the band edge, both amplitude and phase change. The orange vector on the left is the transfer function, that is, the complex ratio of the output versus input. The vector length is the relative gain, and the green angle is the phase. Observe how it changes through the frequency range around the approximately 3.5 kHz resonance. Use the app for sanity check while doing experiments. Square wave also allows to check the oscillatory response to a step function. The frequency should be much lower than the oscillatory frequency of around 3.5 kHz so that the response can be easily seen. The Wiring Help app provides step-by-step instructions for the high-pass and low-pass circuits. The wiring is relatively simple and straightforward. This photograph shows a representation of this high-pass filter circuit. A difference from the schematic is the power rails. The plus and minus 12-volt supplies are on two separate inner rails. The ground is on the two outer rails. The photograph is intended to have sufficient spatial resolution and color clarity to allow the reading of the component values as shown, which can be used to build the circuit. Steps A2 to A4 are straightforward and similar to those in Lab 5 and Lab 4. Once the measurement connection is set up, the only differences between the steps are the various waveforms and frequencies. The input test signal and a monitor scope channel should be connected to the circuit input, which is the input terminal of the 0.001 microfarad capacitor. A second scope channel should be connected to the circuit output, which is pin 6 of the op-amp. In a test of the circuit on its own, all other connections to other circuits as shown in the photograph should be disconnected. The circuit frequency response was measured with 45 sinusoidal inputs. The frequency ranges from 50 Hz to 50 kHz. Fine data points were taken near the resonance to study its behavior. The Bode plots are shown on the left. The 3D Nyquist plot is shown on the right. For the Bode magnitude and phase plots, the dots and the solid connecting lines are experimental data, the dashed curves and the model calculation. The model does not include the realistic gain bandwidth of the LM741 op-amp, hence there is some discrepancy at the high frequency end. Also, the calculation uses nominal values of the resistors and capacitors. No adjustment was made to fit the resonance frequency. A square pulse with duration of 2.5 millisecond, which is several times longer than the oscillatory relaxation time of the circuit, was used to measure the step response. The result agrees with the model calculation as shown. When the pulse is constant, whereas before, during, or after, there is zero output, as the DC is filtered out. Only at the abrupt step changes, up or down, does the circuit allow the high-frequency component passing through, shown as root responses of the circuit transfer function. A 10 microsecond input pulse, which is much shorter than the oscillatory time, was used as the impulse input. The output shows the expected Dirac delta function response associated with the transfer function roots. Assuming infinite op-amp bandwidth, the transfer function can be obtained with the node voltage equations. The solution of the 2x2 system of equations is then obtained. The transfer function shows its second-order nature with respect to the complex frequency S. This app calculates the high-pass, low-pass, and band-pass filter circuits. Consider the high-pass filter. A useful item to view is the frequency response, that is, Bode plots for magnitude and phase. There are options for fast plot for slower CPU, and for more elaborate graphics but can be slower. The 3D transfer function graph shows the poles and zeros of the transfer function. One graph is for the magnitude, the other is for the phase. The various contours red and blue are the contours of constant magnitude or phase. The 3D transfer function can also be plot on the log frequency scale. Its projection on the imaginary axis plane is the two-dimensional Bode plot. Lastly, a most useful function of the app is the simulation of the output signals for sinusoidal and step function waveform input. This chart on the left is the two-dimensional Nyquist plot, showing the transfer function as a vector in the complex plane. One can use the app to compare the experimental measurements versus the simulation. It is good to get an idea of the ballpark output to compare with the experimental results as a sanity check. Heuristic design of the frequency response can also be done by varying the resistances and capacitances. Root plot can give a rough idea of the response. Numerical values of the roots can be obtained. Another app works the reverse: input the desired roots, and it calculates the resistances and capacitances to be used.